This is it, the last lecture in the series. Thanks for making it this far. We're going to look in detail at two interesting and useful applications of the singular value decomposition. These will give you a feel for how the SVD reveals the underlying structure of data captured out in the real world. The first application we'll explore is image compression. When we capture an image with a camera, that image is a giant matrix, a 2D array of pixels. If we wanted to save this image onto our computer with the best possible quality, we would need to save every single pixel. The thing is though, we can throw away some of the information in the original image without any noticeable change in the image quality. As we throw away more and more info, the image quality starts to get a little worse, but if we're short on storage, or if we want to quickly transmit the image online, we might want to make a trade-off between file size and image quality. Let's first formulate the problem of image compression precisely. We want to reduce the amount of data required to store an image while minimizing the loss in image quality. We can quantitatively measure image quality by subtracting the original image from our compressed image pixel by pixel, squaring these differences, and adding them all up into one number. The smaller this number is, the closer our compressed image is to the original image. This metric I'm describing should ring a bell. To be specific, we might have an uncompressed image like the one on the left with a file size of, say, 1.4 megabytes, and we'd like to compress it to 1.1 megabytes without any noticeable change in quality, like the image on the right. Now, given that images are just matrices, how might we use SVD to solve this problem? Well, if you think about it, this is just a low-rank approximation problem. All we have to do is perform SVD on the original image, keep the first k singular values, where k is some number we choose depending on our quality versus size trade-off, and multiply the SVD matrices together again to construct the compressed image. That's all there is to it. This low-rank approximation will minimize the loss in image quality, which is just the Frobenius norm of the difference between the compressed and uncompressed images. Low-rank approximation makes our compressed image as close as possible to the uncompressed image while reducing the amount of different numbers we need to store. This is perfect for us. There's just one detail we need to take care of. A color image is really a collection of three matrices, one for each color channel: red, green, and blue. We simply need to apply a low-rank approximation to each color channel separately, so we'll apply SVD a total of 3 times. Here's all the code you need to implement this algorithm. You can find this code along with an example image in the GitHub link in the description. Give it a try. It takes no time to run, and it's literally just a few lines of code. In this Python file, we first load the original image, then we generate 3 different compressed images with different values of the low-rank cutoff k, so that we can see how the quality versus size trade-off looks. In this script, I'm using values of 50, 200, and 500 for k. The example image I'm using has a resolution of 1920 by 1080 pixels, so you can figure out for yourself what the total number of singular values is. In the outer for loop, we iterate through each k value, and in the inner for loop, we have the main part of the algorithm. We loop through each color channel, red, green, and blue, and apply the SVD to each matrix. We set all but the first k singular values to 0, and multiply the SVD matrices back together to create our compressed image. We bundle the compressed red, green, and blue images into one image at the end of the loop, and we're done. As an example, I have here a 1920 by 1080 pixel image of Shibuya Crossing in Tokyo. It's the original image, and it takes up about 1.4 megabytes. Now we're looking at the compressed image using our SVD-based algorithm with k set to 500. It looks identical to the original image, and that's amazing when you realize how much information we've thrown away. If you compare the images very closely, you might notice a few spots where the image quality just slightly degrades. At the bottom right, you'll notice a guy wearing plaid pants. In this compressed image, the plaid pattern becomes just a little more blurry. Still, all things considered, these are some great results. Now this is the compressed image we get with k set to 200. The loss in quality is becoming noticeable now, especially when you look at the billboards on the upper left and right. This is actually the 1.1 megabyte image from a few slides ago. When you look at the image full screen like this, the quality degradation is noticeable, but when you shrink the image size somewhat, it's really hard to tell the difference between the compressed and uncompressed versions. If you're making a YouTube thumbnail, for instance, this amount of quality loss might be acceptable. At this point, we've thrown away most of the information in the original image, so I think it's incredible we still have this much clarity. Finally, here's the compressed image for k equals 50. The image looks pretty bad now, but we've thrown away nearly all the data at this point. Think about that. With just a rank 50 approximation, we can still see the general shape of buildings and people, and we can still read the Forever 21 logo. If you're training an AI model, and you want it to generalize well, this sort of image might be useful. This amount of compression throws away a lot of minor detail and keeps broad shapes and colors, and that's what's most important for a lot of classification and detection algorithms. It's also a fast way to create noisy images to prevent the AI model from overfitting. With this much savings in terms of data size, it would make training a lot faster too. The key thing to take from this is that information is often unevenly spread across pixels of images. Images are just matrices, so SVD and low-rank approximations help us exploit that information asymmetry. Now we're going to look at our second application, 3D reconstruction. This involves determining the 3D structure of an object from pictures. Before we state the problem precisely, let's explore what it means to take a picture in mathematical terms. Imagine we want to take a picture of some object in the real world, like this 3D colored box on the right-hand side. We point our camera at the object, and the camera is represented abstractly by a point called the camera center and a rectangle called the image plane. We imagine light rays coming from the world toward the camera center. Specifically, light rays from the sun or from some light source are being reflected off of the object face in all directions, and some of these rays will point toward the camera center. On their way, these rays will intersect the image plane at specific locations, and together, the shape they make becomes the image of the object. We say the object is projected onto the image plane, so in this way, we take 3D information and project it onto 2D information in the form of pixel locations. The light rays have varying intensities, so the corresponding pixels will be brighter or darker, and the light rays will have varying wavelengths, so the corresponding pixels will be one color versus another. In what follows, we don't need to worry about the details of how the intensities or colors are determined. What we're concerned about is the pixel location that corresponds to a particular point on the 3D object. Here's the same setup from a different angle. The point capital X, Y, Z on the right-hand side is a 3D point on the object we're taking a picture of. We imagine a ray joining this point with a camera center, and the place this ray intersects the image plane becomes the 2D pixel location lowercase xy. In general, the process of image capture can be hard to realistically model, but for our purposes, image capture can be modeled by a matrix equation if we make what's called the affine camera approximation. We assume the camera and the object are far apart. We then get this simple matrix equation. I'm not going to derive it, but you can find the derivation in any standard textbook on computer vision. Instead, we're going to take this equation as given and see how it can help us perform 3D reconstruction. On the left-hand side, we have a 2-vector of the 2D coordinates of a particular pixel, and on the far right, we have a 3-vector of the 3D object point that represents the corresponding point on the real-world object. And in the middle, we have a camera matrix, a 2x3 matrix that transforms 3D object points to 2D image points. There are no restrictions on the elements of the camera matrix, except for obvious edge cases like making all the elements 0. You can put any 6 real numbers you like in this camera matrix, and it will physically correspond to an affine camera with valid physical properties. Note that the camera matrix depends on the camera's position, orientation, and focal length. When you point your camera at the object, if you've set up your camera with a certain lens, and you've placed your camera at a certain position and orientation relative to some coordinate system, then there's a straightforward way to calculate the elements of the camera matrix. On the other hand, if someone sends you the elements of their camera matrix, and they don't send you anything else, they don't send you any images or any object points, then just from that camera matrix, there's a straightforward way to calculate the focal length, position, and orientation of that person's camera. We won't go over how this calculation works because we won't need it, but just be aware that it exists. To simplify the notation, people often write the matrix equation this way. Obviously, lowercase x represents the 2-vector of image points, capital M is the camera matrix, and capital X is the 3-vector of object points. Now, instead of just thinking about one point, let's think about several. The object points and the image points for one image can be grouped into one equation like this. Let's say we have n different points of interest on our object. On the left, we have a matrix whose columns are the image points, so the shape of this matrix is 2 by n. On the right, we have a matrix whose columns are the corresponding 3D object points, so the shape of this matrix is 3 by n. We can generalize this to multiple images. If we move the camera to different locations and tilt it at different angles, the camera matrix M will change. We'll put a subscript on the camera matrix to denote which image it refers to, and we'll put superscripts on the image points to denote the image index as well. We won't make any changes to the object points because we assume this object is stationary, and we're just moving the camera around. This means the object points are the same for all images. If we take a second picture, we'd write it like this. And if we take m pictures, we'll have one matrix equation for each value of m. Now we're ready to precisely formulate the 3D reconstruction problem. We have a stationary object. It could be anything, but for simplicity, you can just imagine a box. And we move the camera around it and take several pictures. Let's say we have no idea what the object points are. We don't know anything about the dimensions or the structure of this object, and we don't know anything about our camera. We don't know the rotations and translations of the camera shown here. For example, your friend takes these pictures and just hands you the images with the image points labeled, but they don't tell you where they took the pictures from or give you any info about their camera. Now, just from the images, can we recover the 3D structure of the object? This is called the structure from motion problem. We place a camera at various positions and orientations and capture images of a stationary object, and given only the image points, we want to recover the object points. Note that the image points across different images have been matched and organized for us. This might seem like a big assumption, but it's actually not unreasonable at all. There are lots of established tools out there for performing what's called key point matching. One famous algorithm is the scale invariant feature transform, or SIFT. I won't explain any of these key point algorithms here, but I'll leave a link in the description for a SIFT implementation for anyone who's interested. Just be aware that key point matching algorithms exist, and they're routinely used. Now before you keep watching, I encourage you to pause and think about how to solve the structure from motion problem. The solution is very short. Okay, ready? Here's the key. The only data we have are the image points, so let's first arrange them into one big matrix. Each row represents one image, and each column represents all the image points that represent the same unknown object point across all images. This means our matrix has 2m rows and n columns. Then we just use the SVD to find the rank 3 approximation. Why rank 3? Because then we can split the matrix into a skinny matrix holding the unknown camera matrices and a fat matrix holding the unknown object points. The camera matrices have 3 columns and the object points have 3 rows. If you write out the matrix equation row by row, you'll see we've recovered the equations from a few slides ago. This is all we need to do to recover the object points. Or is it? You'll notice the singular value matrix is missing. We know we should truncate the singular value matrix by keeping only the first 3 singular values, but where does it go? It looks like we've either multiplied the singular value matrix with the camera matrices or with the object points. Which one is correct? Well, that's an ambiguity inherent in the problem. Without additional information, we don't know where to absorb the singular value matrix. What this means is that we can only recover the object points up to an arbitrary scaling. If you think about it, it makes perfect sense. Physically, this means that if someone hands you pictures of the Eiffel Tower, you can't tell whether it's the real-life Eiffel Tower just by looking at the pictures. It might just be a hyper-realistic miniature version of the Eiffel Tower. Unless you have some way to determine absolute distances in the pictures, it's impossible to tell these two situations apart. A simple way to set absolute distances would be if you saw people in the pictures and you knew their heights. From that additional information, you could appropriately scale the object points you recovered for the Eiffel Tower so that you match the Eiffel Tower's image points and you match the image points and actual heights of the people. If your data for the people's heights are very accurate, you can determine the scaling accurately, and from that, you can recover the actual dimensions of the Eiffel Tower very accurately. It's really interesting how there's an exact physical phenomenon that corresponds to ambiguity in the math. It might take a minute to fully grasp this solution because it involves arranging the image points into a matrix in a clever way. Except for the caveat about absolute scaling, this is really all you need to recover the object points from the image points taken by an affine camera. I encourage you to study this algorithm and see if you can find the minimum number of pictures and the minimum number of key points you would need to reconstruct a 3D object? There's a very simple answer. Believe it or not, there's actually a connection here to biology. Leave a comment if you think you figured it out. By the way, this SVD-based algorithm is known as the tomasi-kanade factorization in computer vision. It relies on the affine camera approximation, which is not always a reasonable approximation to make. More realistic camera models take into account perspective effects and lens distortion. But this factorization algorithm is still important to study since it's the foundation for more advanced reconstruction methods. Fun fact, Kanade was my former boss's PhD advisor at Carnegie Mellon. Now it's time to see what this thing can really do. This paper by Snavely et al. Is one of my favorite papers ever written. It's just fantastic, and it's an easy read, so please check it out. The idea here is to use publicly available photos taken by tourists to reconstruct 3D models of famous sightseeing spots. Obviously, the authors of this paper had no information about the cameras used to take the photos. They're just photos literally taken by randos. But just from the images and from key point matching, they were able to achieve ridiculous results. Here's the famous Trevi Fountain in Rome. On the left is an example of one of the photos they used, and you can see the quality isn't great, but that didn't matter. On the right, we have the reconstructed model shown as a massive set of 3D points. In the foreground, you'll see these little pyramids all pointing toward the Trevi Fountain. These are the estimated camera matrices. Here's the Colosseum. The reconstruction accuracy here is just absurd. I can't express how much this completely blows my mind. There's no AI involved here. This is just straight up linear algebra. Finally, we've got the most impressive one. This is Half Dome in Yosemite, California. The other locations are man-made structures, and from historical records, we might be able to get a rough idea of the dimensions, and worst case, we could just get a bunch of people to climb up and measure the Trevi Fountain. It would be a lot of work, but it could be done. Not Half Dome though. It's enormous. It's got all these steep slopes and angles. You can't just climb up to any spot you like unless you're Alex Honnold. This really showcases the power of 3D reconstruction. In addition to preserving accurate 3D models of historical structures that'll one day get worn down or possibly destroyed, we can use these models in virtual reality or video games or movies. Much more accurate methods for reconstruction have been developed since this paper came out, but this is a landmark paper, and it shows how much you can accomplish just by manipulating vectors and matrices. So that does it. You've made it to the end. You should be proud for making it this far. You've got a deep, intuitive understanding of linear algebra, and you've seen all the different ways it can be used to solve real problems. So where should you go from here? There are a few different routes you can take. For the most part, we've stuck with real numbers throughout this course, but the results of linear algebra are easily extended to complex numbers. Complex linear algebra should be easy for you now, and it'll give you a more rigorous view of what we've covered and open up a variety of new applications. Historically, one of the most important applications of linear algebra is quantum mechanics. When quantum theory was being developed in the first few decades of the 20th century, physicists found that the laws of quantum mechanics were most easily expressed in the language of matrices, but very few people at the time knew any linear algebra. Not you, though. Quantum mechanics is incredibly interesting and incredibly weird, but you've got the hardest part out of the way, which is the math. To tackle quantum mechanics, you'll need to learn some complex linear algebra and something called Dirac notation, but if you crack open any standard quantum mechanics textbook, you should find everything you need. If you have an interest in quantum computing or material science or particle physics, you'll benefit from building a strong background in quantum mechanics first. Another fun route is numerical linear algebra. If you're interested in computer science or algorithms, you'll want to look into this. This field is all about how to implement efficient and low-error algorithms for matrix operations. This is what makes GPUs fast. If you're interested in computer graphics, fluid dynamics, or just fast computation in general, you'll benefit from learning about numerical linear algebra. Finally, any sort of advanced probability and statistics will make heavy use of matrices. There's an interesting field called random matrix theory, which lies at the heart of applications like machine learning. If you want a deep understanding of how AI algorithms actually work, it's essential to build a strong background in probability theory with matrices. And there you have it. I'll be making more videos and courses, so if there's a specific topic you'd like to see, please leave a comment. It could be math, physics, biology, chemistry, or AI and machine learning. Let me know what you want to learn about. And again, thanks for making it to the end.